all that stuff. It's all solved by L'Hopital. So that is a very temporary solution. And plus, I hate memorizing things without understanding why they are those things. So for those of you that aren't here today, I did give a warm-up today with those two problems on it just to get you started. Today, L'Hopital's rule deals with something called indeterminate forms. Now, I would give a definition of indeterminate, but it just means we can't determine it. There are only two indeterminate forms that L'Hopital's works for. Contrary to popular belief, there are only two indeterminate forms that L'Hopital's works for. There are two forms of the limit L'Hopital's rule works for. Two limits L'Hopital rule works for. One is 0 over 0. And it's kind of weird. 0 over 0. If the limit of the top is going to 0, the limit of the bottom is going to 0. The answer could be a number. The answer could be 0. The answer could be infinity. The answer could be negative infinity too. All three are possibilities. I had Jenny Hall in BC last year who absolutely never believed me that 0 divided by 0 could be a number. It just depends on how fast one is going to 0 and how fast the other is going to 0. And what's L'Hopital's going to do? It's going to turn it from a position problem to a rate problem. So not where are you, but how fast are you getting there? Whichever one's going faster, a sloppy way to say it is the winner, but that's who determines the limit. Whichever one's getting there faster. The other indeterminate form is infinity over infinity. Which can include negative infinity too. It's like negative infinity over infinity is a form we can use for L'Hopital's. Infinity over negative infinity is a form we can use for L'Hopital's. There are 4 other forms that we could use. 4 other, let me make sure, 4. 1, 2, 3, 4. Oh, there's a 5th one. 5 other forms that we will use for it, but we have to get them to look like that. In other words, we have to use algebra, common denominators, properties of logarithms to make them look like one of those two. Those are the only 2 that L'Hopital's works for at the end of the day. Now, kind of the weird part of this, I'm kind of going back. How many of you were able to find both of those limits using L'Hopital's? How many could get the top one but not the bottom one? How many of you, I've never heard of L'Hopital's except Beckman talked about it a couple times.
Kyle.
That's like a glorious moment. Okay, so anyways, I'm glad you took this class so you could learn about it, because how could you go to college and not know that? That's like, I don't know. How could you get a date at college without knowing that? Okay, so what are we going to talk about with this today? Talked about that, talked about that, talked about that, talked about L'Hopital's working for that. We will have to use algebra for the rest. So in other words, we can get it to look like that. Hi, I know you guys are going to be late. We can get it to look like that. And notice I was kind of stalling there for a minute waiting for you guys. We can get it to look like that, but we have to use algebra for the rest. The second, and enter without talking. You don't come into a band concert and talk. First one is, if you come in late and you start talking, Carpenter will just start throwing batons at you. And then he'll say, yes, here's a knife. This could be a baton too. Catch. Yeah, he would. Have you ever been late to something for Mr. Carpenter?
Oh my God.
Yes.
We just cut someone from Symphonic because they didn't show up on.
That's their fault. Maggie, that's their fault. They shouldn't have showed up late. Hashtag early is on time. Late is late or what am I? Early is on time. Late, yes.
Late is on time.
Don't be that guy. All right. The second thing is you consider the top and bottom separately. This is going to feel weird because you're going to say L'Hopital's is a quotient rule thing. No, it is not. We consider the top and the bottom separate. And for those of you who just walk in, let me move it down so you can see everything that I covered. There's a small warm-up if you want to watch it, watch the video. But basically, I was just seeing what you learned about L'Hopital's last year, which unfortunately made me sad that a small subset of you didn't even get to experience it. It's like one of the greatest things calculus does. But I guess you didn't talk about limits, so why would you talk about L'Hopital's? That makes sense. No, don't you wish you had a smarter teacher that could figure that stuff out quicker? Okay, so what's L'Hopital's going to do for us? It will determine if these indeterminate forms actually have a limit. Because it is possible that the top and the bottom are both going to infinity, but yet there is actually a limit that it's getting close to. Why do we like this? So number one, we don't have to memorize both Betsy. Number two, because we're way quicker at taking the derivatives of these things than we are those algebraic rules we did at the start. If you remember, Luke was messing around earlier about why I didn't just use L'Hopital's, because I wanted to make sure you knew the limit rules as well. want to send you incompletely to Calc 3. Especially because at some schools, like, 5 minutes away from here, we know the profs that work there. And if they said, why didn't you teach him the proper limit techniques? They could come actually find me. The rest of you are going to go to colleges, well, they'll just cuss about high school teachers not showing the real hard stuff of calculus anymore, just teaching the easy stuff. But if they're right up the road and their kids are in my class, it's hard for me to dodge them. Yes. Could also include negative infinity. So infinity over infinity, it could be negative infinity or negative infinity, negative or positive, positive or negative. All of the combinations of infinity work for that because we can't determine where it's going. We have to determine where it's going, which one's going faster. So what did our friend L'Hôpital, by the way, it is not hospital. If you really want to sound dumb to your college prof, go be like, we took the hospital to that problem. The L hospital to that problem. Yeah.
L hospital.
Okay, there's some people that don't know how to pronounce this and would say that. We took the hospital route. No, we didn't. We took L'Hôpital. It is French if you don't know.
Your prof is going to send you to the hospital.
Oh, except I forgot. What is the thing called?
French hat.
Triangle? No, it's only got 2 sides, Josh. Come freaking on. It's the what?
Circumflex.
Yeah, I remembered that when I was in high school French too. So one time we use it in math in L'Hôpital. Okay, so if we have an indeterminate form, what do we do? Shh, what do we do? What do we do? Okay, so if you have the limit as x goes towards infinity, but I'm going to put a because it could be also towards a number. It's not just good at infinity. It could be any point a. And we remember the rigorous definition I gave you at the start of the year. The limit of f of x as x approaches a is equal to L if as x gets infinitely close to a or arbitrarily close to a, f of x gets arbitrarily close to L. Well, we got this one. We've got f of x over g of x, which we know by the properties of limits we can break up like it's the day after homecoming as x goes to a of f of x over the limit as x goes to a of g of x, if that is in one of those indeterminate forms, like infinity over infinity. That's b and b, bad news bears. Why? Because we don't know what that's equal to. What do we do with that then? We take that and we then use L'Hôpital's rule. That if it's in that indeterminate form, the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of the derivative of f of x over the limit as x approaches a. Can you still see this? No, you can't. The limit as x approaches a of g prime of x, if and only if it was in that indeterminate form, infinity over infinity, 0 over 0. If it's anything else but that, we have to use algebra to make it look like that first, which is the hard part. Unfortunately, a lot of people will teach this very easy part of L'Hôpital's, but the fun part is if you've got like infinity to the 0 power, how do we make that look like infinity over 0 over 0? Yeah. That's where we get into the fun. Can I go on? Yes, Caleb.
Math question. Can't you use double-sided arrow for it?
Yeah, I could. Same thing. Okay, so let's take a look at example number 1. Let's have some fun with some L'Hôpital problems. Do we want an easy one or hard? Let's go for a medium one first. Let's go for f of x. No. What do we want to do here? What do we want to do? Yes. Here we go. The limit as x approaches 0 of an old friend. You ready for this? Remember I told you. Why do you steal my thunder like that? Okay. Of course it's classic. That's when you go to college next year, if you end up having to retake this class for some reason and the prof goes through this and says, this is a classic problem, you can raise your hand and say, it's so classic. My high school teacher went through it last year as an example of a classic problem. Okay, so we told you at the start of the year was equal to what? 1. But here's the bad news. The top, as x gets close to 0, what's the top getting close to? 0, right. What's sine getting close to as x gets really close to 0? Yeah, remember, sine is going to 0 degrees. Sine is the vertical amount, so you're looking straight forward. How much is that equal to? 0, right. What's x getting really close to as x gets close to 0? 0, right. So this is getting close to 0 over 0. Bad news bears. That's an indeterminate form. L'Hopital. The actual reason we can prove this is L'Hopital's. Otherwise, it's just intuition that the graph. Remember I told you in chapter 1. Guys, stop talking. You're ruining my thunder. If you want to talk, yeah, cough out the hole. If you want to cough. What? Are you okay?
You kind of sound like Kobe, because when people cough, Kobe's like, get out, get away from it, go away.
Yes. Shh, stop talking. So I told you at the start of the year, we just had some intuition that the graph was getting really close to it, but that wasn't really a valid reason. Like, I think it's getting close to there. Sort of like Luke thinks that I think the airplane's going to be okay in that situation. But here's the actual proof of why it's equal to 0. So we break it up into the top and the bottom. And we take the derivative of the top. Now, you're going to say to yourself, quotient rule, quotient rule. People, this ain't a freaking quotient rule problem. We take a look at the rate of the top and the rate of the bottom, and we compare them. Now, I know on your test, you're going to try to make these hard and turn them into quotient rule problems. If you're doing L'Hopital with the quotient, you are making this hard. This is nice and easy. L'Hopital did all the work for you. Take advantage of it. What's the derivative of the top equal to? Cosine of x. Negative or positive? Positive, right. What's the derivative of the bottom? 1. What's the limit of cosine as cosine gets really close to 0? 1. What's the limit of 1 as 1 gets really close to 0? 1, yes. Now, you may ask yourself a question that's going to come up. What if it's still infinity over infinity, or 0 over 0? So bad news. You take L'Hopital. You do L'Hopital, it's still 0 over, or it's still infinity over infinity. You can just keep doing L'Hopital as long as it's in that indeterminate form. It's like we've taken the problem, we've moved it to another problem that still can be used for L'Hopital. We can use L'Hopital as many times as we want. If it's x to the 30th over e to the x to the 30th, we can do it 30 times until we get that top down to a constant. You can use L'Hopital's 30 times. That's okay. Not good for the rainforest, but good for you. Stop and check out questions on that. So ladies and gentlemen, that's why when you go to college, you can say the limit as sine x over x gets really close to 0 is equal to 1, because we use L'Hopital's to analyze how fast is the top going to 0 and how fast is the bottom going to 0. And it turns out which one is going to 0 faster if it's equal to 1. The top and the bottom, which one's going to 0 faster if the limit's equal to 1 of that fraction? If the bottom's going to 0 faster, wouldn't we get a number bigger than 1?
Yeah.
If the bottom is going to 0 faster, wouldn't we get a number smaller than 1? So their rates are relatively what? Relatively equal, right? Those rates are very similar. The rate at which sine goes to 0 and x goes to 0 are very similar to each other. Because you remember back from pre-calc, did that prove that when it was really close to 0, sine really looks like x? Remember, your pre-calc teacher back said, if x is really close to 0, the graph of sine x and the graph of y equals x are really similar to each other, and that's why those properties hold?
It's called small.
No idea what you're talking about? Well, they probably mentioned it, but it was like a really tiny detail of that day, so yeah, you probably forgot about it then. So let's stop and check out. Questions on that so far? Ayana?
Can you just repeat why you take the limit of the derivative?
We take the derivative of that limit, just the limit stays inside of it. Because what L'Hopital really found, like in his proof, if remember I talked about advanced calc, which is a glorious thing, because you go back and you prove everything from calc. Prove it from scratch. What L'Hopital looked at is they're both going to infinity. But as you look at the graph, like there is a bound on its growth. So like this, let's look at e to the, let's look at x over e to the x. So L'Hopital, remember back in the day, you had to do everything by hand. So he looked at the graph as he plugged in really large numbers, and he noticed there was an upper bound on it. In other words, there was a number that e to the x over, no, what did I say, x over e to the x? X over e to the x was always below, no matter how large the numbers you plugged in were. So a limit existed, but we could not find it just by substitution or algebra. So what he said is, look at the rate of the top over the rate of the bottom and see which one of those is going to infinity faster. And it turns out we can actually analyze the limit, which is what he proved, by taking the derivative of the top over the derivative of the bottom. In other words, analyzing the rate at which the top is going to a number and the bottom is going to a number, and then comparing that to find the limit, which works. Shockingly. I know, imagine dating that guy and he takes you out to dinner. He's like, guess what I found out today? We don't have to worry about these limits we can't figure out no more. I figured out what they are. And then he just talks for 4 straight hours about that and shows you the proof. And you're like, no, just give me the prime rib. Let's cut to the chase. Let's get this date over with. And he just keeps talking about it. But yes, let me give you one to do. I'll take your question, but let me give everybody one to do real quick. So what if it's still infinity over here, infinity? We do L'Hopital again. In fact, like a problem like the limit as x goes to infinity of e to the x over x to the 30th, how many times did we have to do that? How many times do we have to do that to actually be able to find it? Yeah, we just do that 30 times. Do L'Hopital's 30 times. Imagine that being your homework at night. Like you have to do this reiterative process 30 times to get the answer. But here's the deal. E to the x, what's the derivative of that always going to be? E to the x. X to the 30th, it will give you 30x to the 29 and then 29 times 30x to the 20. And there's going to be a giant coefficient in there that's going to convince you that that's going to infinity faster. But exponentials almost always win. An exponential has to have a base less than 1 to lose to almost anything. And that, again, connects back to that finance project. That's why you want to start saving on the very first paycheck. Because the thing that matters is how many times you save, not how much you save each time. Exponential growth is very hard to beat. You can take advantage of it by saving on the very first paycheck. But this one, if we took the derivative 30 times, the derivative of the bottom would be a what? Constant. Would it be big or small?
Very big.
In fact, what would it be?
35.
Done! Real quick, what would that constant be on the bottom? 30 factorial, right? 30 factorial, good job. It would be 30 factorial, which is a very big number. You'd love to have that much in your bank account. The top would be e to the x. So you'd have e to the x over 30 factorial, infinity over 30 factorial. Unfortunately, even though 30 factorial is big, it's not growing without bound. There is a limit on it. That's why it goes to infinity. But I want to give you one. Let's have you do an example, and then I'll take some questions as you're doing that example. Let's take the limit as x goes to infinity of what should we do? Let's do a fun one. Let's do 2 to the x over the natural log of x. Hot dog. 2 to the x over the natural log of x. And what's that limit equal to if the limit exists? Ayana, question.
So going back to the first example, what if after you did the whole L'Hopital was 0 over 1, but the answer be 0 or would it be 1 because it's, no? So your answer is it combined. You're not choosing which one goes.
Well, what it's saying in that case then is the rate of the top is very small, the rate of the bottom is 1, and very small over 1 is going to go to 0.
So you're not going to take the rate of the bigger one.
It's weird. So your original one just analyzes the position. Where are these points at? When you use the L'Hopital now, you're analyzing the rate, but we find the limit using the same properties. So once we take the derivative, then it's back to being a limit problem that we just treat like a limit like it always was. So even though it's a rate now, not a position, the limit rules we use to actually determine the limit are exactly the same. And that's where the L'Hopital saves our butts on some of these problems, because there's no way we can analytically solve it unless we look at the rates of the top and the rates of the bottom.
Okay. So
Now, oh, sorry, keep going.
So when we're doing, when we're taking the limit of anything as it approaches infinity,
Yep.
basically doing the whole, just about right.
Unless you can determine it anyway. Like if you have x squared, you're not going to use the L'Hopital's. You're going to use, it's going to, as x squared goes.
No, but like when we look at it, and we think faster.
Yep.
we're using the-
Exactly.
Okay.
In fact, are you ready for stuff like this? Like in the warm-up, I had x sine of 1 over x, which we used the sandwich theorem for earlier this year to like squeeze that limit between two things. Now we can just use the L'Hopital's because they're, sine is going to 0, x is going to 0, it's 0 times 0, but ooh, how do we make that one of those indeterminate forms that we talked about? Because we can only use L'Hopital's in two situations, if it's 0 over 0 or infinity over infinity. We are going to use algebra to take situations like 1 to the infinity, 0 to the infinity, infinity to the 0, and make them look like infinity over infinity. And that's the buggers they throw on the AP test, is they give you like a trivial L'Hopital's problem, and then they give you this absolutely crazy problem that you're like, how do I take that limit? And then you think, oh, but I got to make it look like one of those two L'Hopital's indeterminate forms. And then you just say, oh, that's a pre-calc problem. It's not a calc problem. In fact, a lot of you, if you Breebach spends an insane amount of time after the seniors are gone using limits. And You could have done that last year in Bree-Box class, but you're going to be loving how you can do it with their friend L'Hopital. I know a lot of you are thinking like right now, like L'Hopital would be an awesome prom date. You're right. You're right. He'd solve a lot of life issues for you. Or at least he'd be able to tell you the rate of those life issues. Let's talk about this. Ideas. What should I do? Well, what's the top going to? Infinity. What's the bottom going to? Now, just real quick, in the back of your head, what's the graph of 2 to the x look like? What's the graph of ln x look like? Yeah, so we probably know the limit's going to go to where? Probably going to go to infinity, but how do we actually show it? We have to use L'Hopital's to do that. So the top and the bottom are both going to infinity. So infinity over infinity. So we have an indeterminate form. See why calculus is so fun? Like these horrible, horrible problems. You have these nice, easy solutions for them. And then your parents ask you, like, what did you learn at school today? And you tell them something like that. And they're like, man, my kid's freaking smarter than me. Can I still take his cell phone? Oh, yeah, you can. Yeah, you can. Okay, so we take the limit. So we take the limit of the top, its derivative, over the limit of the bottom's derivative. Okay, the limit of the top, 2 to the x. What's the derivative of that puppy? Ideas. Volunteer, what's the derivative of that? That's that blank rule problem. That's a blank rule problem. Is it a power rule problem? No, it is a chain rule problem. Every problem we do all year is a chain rule problem.
I can't get that wrong.
Exactly. Today was the day in AEB that I show them that every problem we've done all year is a chain rule problem by giving them something ridiculous like x squared and showing them it actually was a chain rule problem. We were just multiplying by 1 the whole time. And then, yeah, exactly. Brain matter all over the place. So we had to clean it up during the assembly. What other rule are we using on this one? This is a
implicit. You can make it implicit.
You can make it implicit by taking the natural log of both sides, but we don't want to do that. That's hard. Where's the constant in this? The base of the variable? Yeah, it's a constant base rule. It's a constant base rule. So the constant base rule is the derivative of 2 to the x is 2 to the x times the log of what? ln. Good job. It's the natural log of 2 multiplied by the derivative of the x, which the derivative of the exponent, which is just 1, right? The derivative of ln x is equal to what? 1 over x. Now, question to you. What's that going to? What's that going to? Ideas. Do we have to use L'Hopital? No, infinity over 0 doesn't work. Ideas. Ideas. Yes, kid.
Fraction in the denominator. You can just put the fraction in the numerator.
Can I take the fraction out of the limit, though?
You can pull the limit out. Limit on with the fractional rule. If you have a limit of a rational function.
Yes. We can go one way. We can take the limit and break it up into the top and the bottom, but we can also take the limit of the top and the limit of the bottom and bring them back into 1. And that's why exactly I do this problem every year. You can take the limit and break it up into the top and the bottom, but you could also bring it back together as long as it's the limit of the same thing, limit of infinity. So we can bring this back, and that's the killer play for this one. Otherwise, you can't do this one. So we bring the limit back together. So then we just have the top, we have the bottom, now what can I do with that denominator?
Reciprocate it.
Yes, copy that reciprocal. We take the reciprocal of that, so it's a limit as x goes to infinity of 1 over x, which is just going to give us an x, times 2 to the x, times the ln of 2. Now, that's algebra. Let's stop and check up that, and then I'll talk about the limit in just a second. But let's talk about the algebra first. Freaking exciting day. Like the amount of stuff you can do after today, it grows without limit.
Like land a plane faster.
It's what?
Land a plane faster.
And overrun.
Not really a good analogy. I do questions on the algebra. Shh, guys, stop. I want to take questions on the algebra. Questions on the algebra. Sublime, are you with me? Okay. Questions on the algebra. Okay, now what's the limit of that? Well, what's this going to? What's that going to? And what's that? Yeah, infinity times infinity. Turns out it's, yeah. Now, here's what you have to give up. Sometimes the limit of infinity over infinity is infinity. Sometimes infinity over infinity is 0. Sometimes it does not exist. And sometimes it's equal to an actual number. L'Hopital's is what helps us determine that, what's in that indeterminate form. L'Hopital's is what helps us to do that. All righty, stop and check out. Questions on that? E to the x, 2 to the x, a number that's greater than 1 to the x is very hard to beat. L'Hopital's will tell if it gets beat, though. Why is it hard to beat it? Because it's always going to return an exponential every single time. It's always going to return an exponential every single time. So it's hard for it to lose unless it's less than 1. And of course, a number less than 1 to the x power is just getting smaller and smaller. Smaller instead of larger and larger. And again, every time you go to a bank, you should think about that. You should think about it, man, L'Hopital's told me exponential growth is hard to beat, so I can't wait for this bank to give me exponential growth. Yeah.
What would be exponential?
The bigger exponential.
Yes, don't do it, you get points off.
Hold
I'm not gonna let it go.
on to that point. Hold on, Caleb.
This is like some of the stuff we're talking about, rates to top, rates to bottom, infinite series, and then you have to talk about bounding from above.
And that, again, this is, you may say, Beckman, why didn't you torture the kids with that last year? Yeah, I made a strategic mistake and let them get away with that build Betsy stuff at the start of the year. And then when I got to chapter 9 of this book, it absolutely killed me. Because then I had to go back and teach all the actual series and sequence stuff with the limit stuff, and it's just way too much for kids to up on me. Which, frankly, I didn't blame them because I did tell them at one point, like, I shouldn't have let you get away with that. I should have made you learn about the limit stuff. Because again, Calc 2 is really hard. Kaylee Todd, if you remember her, she graduated last year. She's in Calc 2 at Utah State right now. She called a few days ago to ask, so does math get harder than Calc 2? And I was like, not for a couple of years. So if you can get it done in high school, you got a big advantage. Calc 3 is a piece of cake compared to it. Differential equations is a piece of cake compared to Calc 2. Kiwi.
So how is infinity over infinity a constant?
Infinity over infinity can be a constant because we are both going to infinity, but the rate at which one goes to infinity can be bigger than the other.
You'll have to do something other than what L'Hopital said to what that constant is.
No, L'Hopital's is the only way to determine what that constant is.
Okay.
Because that analyzes the rate at the top over the rate at the bottom. Okay, are you ready for the harder stuff, or you want another example to do on your own kind of this hard?
Harder.
Harder? All right. Yeah, let's do one of these. L'Hopital? Yeah. Do you need more? That's a big advancement in your math career today to say that's the only thing we're going to. Yeah, the algebra ones make it a little bit harder. The algebra ones make it a little bit harder. Let me think of something good, or is there something good I can find in the book here? Oh, yeah. Let's go for one. Let's go for one. Let's go for example. Is this number 2 or 3?
3.
3. Let's go for the limit. What should we go for? What should? Yes. Oh, yes. Yep, 10x over, what should we put on the bottom? X squared or 10x? Let's go 10x. 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 Like a heart attack, get to work. Luke, get to work. I'm just giving you a hint of what's coming. The Air Force Academy isn't a big fan of kids talking in class or talking period their freshman year. Right? Okay. Well, he's on break. Does he talk a lot more when he's home? What's that? Gotcha. Does he have a lot to say? Because he doesn't get to talk Monday through Saturday. And if he does talk, it probably leads to push-ups anyway. So.
What is?
I can make it harder. We can do 10x squared. Okay. Yeah, just 10x. Yeah. You just look so disappointed, like it should be harder than that. Yeah.
Zero.
Yeah. I must,
Actually, let's give you 2 to work on. 2. Let's go for one more. Example 4. What else can we come up with? Yes, limit as x goes to 0 of yeah, let's go for this. Sine x minus x over x squared. Ready, set, go.
Wait, that says sin x minus x.
Sine x minus x over x squared. That's another fun one. Because you think you're done, but you're not quite yet. Because the derivative of x is 1. I know.
Is that
I know.
sin x to the negative x?
Sine x minus x. But that would be even. No, we won't do that. That's okay. That's getting a little crazy. There. It's getting a little crazy. What time are we out of this class?
We have a long time. That's why it's 12:55. No,
I'll look. I'll look.
They're 15 minutes short.
Okay, so then lunch and class starts.
Wouldn't give us a
We gotta do it twice.
Yeah, we get out of here at 12:50.
Thank you, Ayana.
55. You sure? 55 seems too long.
Actually, I think it's 45, and we have a 10-minute pass. See, look. I think it's 45, and then we have a 10-minute passing.
Yeah, you're right. It's actually we get out at 45.
The 10-minute pass.
Yep.
So
So
we
you're
have
on
a 10
Hatchell's
minutes.
like district improvement committee.
I'm on like every committee. Like actually, I'm on like the
We should
youth
talk.
law enforcement one
We
too.
should talk. Issue.
About what? Managers winning? Oh. Okay. They just don't like DCC.
Okay, I'm sorry. I cannot buy that. This is like the easiest teaching job I've ever had. Ever. You guys want to learn. You're excited to go places in life. The biggest thing I have to do is remind kids they're not going to be able to talk to the Air Force Academy next year, so they shouldn't talk this year. Hashtag don't learn bad habits. In fact, if I had given these 2 problems in the last school I worked at, they probably would have reported me to the principal. Like, you can't assign stuff that hard.
At my school in
Really?
Virginia, teachers weren't allowed to give you below 50% on anything.
Oh,
And
yeah.
50%
In my previous school, if you got a 5% on a test, a 60% went into the grade book. So it didn't matter if you got a 59 or a freaking 4. So a lot of kids would like look at their test and be like, I can't pass this. So they just turn it in with nothing on it. I'd be like, this is the best rule ever. I don't have to grade it. Yeah, I'm so excited.
Oh, that's so.
I really like the
Seriously,
50%.
if you turned in a test blank, you got a 60%.
No.
So
Yeah, that's
kids-
how it was in Virginia. Like, I can't
Yeah.
get below 50%.
Yeah.
anything.
So kids would look at their test and be like, I can't do this. Or like, I can't get a 60%, so I might as well turn it now because I'm going to get 60%. In fact, you get a 40, and imagine the poor kid who gets a 45% who actually did the test. And you feel so bad for him because if he had done nothing, he would have done better.
Oh, no. I think it was.
Yeah, I know. We'd still put in the 60, but yeah, when I got there, I was like, man, some of my friends would have had way more free time in high school.
What classes did you teach at your
Okay, when I was teaching in the intercity, I taught integrated math 1. I know some of your parents were here when we at DCC had integrated math, which is way before I was here. Integrated math 1, integrated math 2, integrated math 3.
What are those?
So there are these books that actually for teaching in the inner city. Now, some of you I know, I'm going to show you this book, and your parents are going to be like, okay, so these are the books that DCC opened the school with. Do your parents know these, Will? Okay, so this is a great book to teach in inner city, because if you don't know, like a lot of our kids are on like their 4th high school this month, so of course they like if you start in chapter 7, they don't know chapters 1 through 6, so that's wonderful that you're working on something that depends on 1 through 6, but they can't. So what this book does is it weaves together discrete math, geometry, algebra, and stats in a 3-year. So you cover everything you should in algebra 1, geometry, algebra 2. You just do them over 3 years instead of like a year of algebra, a year of geometry, a year of algebra 2. Now, shh, don't go home and tell your parents this. I know it's on the web, but it actually works really well. If you can just get over for a minute that not every kid like has to be able to find the complex conjugate roots of a polynomial. Like they don't have to be able to factor x to the 6th and get the complex roots. And let's be honest, everybody who needs to learn this is in one of my 3 calculus classes, but it actually works really well. And for inner city, because like you start only applications of that ever. And then parents are like, but yeah, so anyway, it actually worked pretty well, but this is what they look like. But they had that there, so that's what I taught in that's what I taught at Richfield.
Why were so many kids like transferring into your class?
Because it's a reflection. Because Caleb, when you live under a bridge and you have to move to another bridge, you might have to move to another school district because your new bridge may not be under the same school district as your old bridge. And a lot of it just had to do with they had really unstable family lives. Like they live with their uncle, then they live with their mom, then they live with their dad, then they live with like some friend, and they're constantly moving. And like I told you guys before, like some of you guys probably are worried about what you're going to get done tonight. How many of you are worried if you will have food available to you tonight? Like no joke, Friday and Monday, almost everybody came to school because they needed food for the weekend. And we had like church charities and stuff that would like hand out food to the kids on the way out the door so they wouldn't starve all weekend. No, yeah, like dead serious. Dead serious. Like Monday and Friday, kids are hawking up lungs or hawking up blood, but they're there because they need food for the weekend. Yeah.
And then you had the metal detectors there.
Yeah, we had to go through them too. Well, you had to go through them every day.
Oh yeah.
Like if you showed up at late work or you showed up to work late, you might not get through the metal detectors on time. So it didn't really matter what class you had first period. So a lot of kids were late because of security, not for any other reason. So yeah, it was different world, but that's how you get your student loans forgiven. So. Right.
In the inner city?
What's that?
Yeah,
you teach math for 2 years in the inner city. Federal government forgives all your student loans. Yeah. Yeah. Taxation's awesome. So, yeah, you like that? Okay, so first one. What's the issue with the? No. Let's get up for a second. Get up for a second. Okay, if you're in this row, you're going to do the first one. If you're in this row, you're going to do the second one. And if you're in this row, you're in trouble. The people on this side are going to do the second one. The people on this side are going to do the first one. Put them up board. Put them up board. This is what other people are doing.
First one, 10x over 10x.
10x. No, Caleb, use the definitive word. It's the limit as x goes to 0. 10x over x.
Why did I do that?
Limit is x goes to 0.
Hey, Cameron.
Yes.
Did you get 0 over
We
2?
only need one.
Yes.
Okay.
Okay. Here, go down.
You go sideways?
Yeah.
November Madness. Chicago 0.
Yes.
Sometimes it just depends on the day.
Good job, Riley.
Yeah, be skinny, people. Be skinny.
Yeah.
Over 10x.
You can work sideways.
Or you know, after.
He's doing my work sideways and I'm taking.
So.
Now you go down. As soon as I
Because
can-
he's on there.
Come at me, Cameron. Let's get it. Go. What happened to your baby?
They fixed it. I don't know why, but humidity's like way better in here now. So.
Right, tax.
Tax X.
Which one's the best? No, it's tax.
And I'm gonna rewrite this. 10 times 1.
All right.
Oh, you know.
We have
The first time we did it.
0.
No, stop.
Square x over. That'll take 0.
I mean, you're gonna half check by.
Problems are so fun. Oh, sorry. Do the question though.
You have 5.
I'm just asking a question.
So Beckman, I'm good for PFS.
Yeah, definitely would.
Yes, you are. All right, volunteer. Who wants to look really smart to the smartest kids in the whole school and explain the first one? Who wants to look really smart to the smartest kids in the whole school besides Caleb? Anybody? Somebody. Don't make me call Arjun in here. Hold on. Oh, hold on. Willow, you talk all the time in class. Willow has beautiful handwriting. We'll wait for her to finish. Can you explain it to us? While she's doing that, who wants to look really smart to the whole smartest kids? Who wants to explain the second one? Is that? Oh, yeah. Who wants to? Yes, first one. Who wants the first one? First one. Sweet. Nick Shampoo. Explain it to us. Caleb, move out of the way.
No,
I asked Caleb to do it.
Oh, go ahead, Caleb.
you guys, come on, this is a fun problem, okay? So we got our initial problem right here. I'm sorry for the work. Somebody was impeding my work line, so I had to go down.
It's impeding your work
So we
line?
take the limit is x approaches 0 of 10x over 10x. That equals the limit is x approaches 0. We get the derivative of top and bottom.
Everybody but Caleb.
Of 10x divided by d by dx of 10x. We get the limit is x approaches 0 of secant squared x over 10. Everybody agree with that?
I agree.
Okay. So then we break it up. Now secant squared x is also the same as 1 over cosine squared x. So we get the limit is x approaches 0 of 1/10 times 1 over cosine squared x. Direct substitution gives us 1 over 10 times cosine squared of 0, which cosine squared of 0 is 1. That equals 1/10 times 1 over 1, which is equal to 1. Any questions? Okay.
Do the full motion. Let's do like a slow-mo camera.
Yeah, can you do that one more time in slower motion?
Okay. Everybody got this, okay?
Okay, Caleb, teaching tip. Everybody got this okay. They didn't even have time to even get their hand up in between. You have to do this thing called wait time. And when you guys are out presenting in the corporate world, when you're out dominating the planet, when you ask for questions, you need to wait for people to ask them so that they get really good ones. If they feel that kind of time pressure, I don't get it. Just so they can possibly get in. Give them time to think about it. If you want intelligent people, intelligence takes time.
Okay,
Caleb, go
pay
ahead.
attention. All right, I'm only going to say this once. I'm an extemper, so I go
I'm only
fast.
going to say this one. Why don't you just say, pay attention, you're going to die.
All right.
I wasn't directed at you.
Ooh.
Gotcha. Caleb, go.
All right, limit is x approaches 0 times. Okay, wait.
Caleb, half speed.
Equals the limit is x approaches 0.
Half of that speed.
D by dx top.
Good.
D by dx bottom. Yields limit x goes 0. Derivative of tangent x. Secant squared x. Derivative of 10x. 10. Does everybody agree with that? 1, 2, 3. Yabe.
Question.
What?
Why are you so hostile towards us?
I know, it's like I'm really mad. Is there
I feel like my ears are being assaulted right now.
Why are you
My ears are being assaulted.
Shall I finish the problem, sir, after your distraction? Moving on to the next step, we can see that the limit as x approaches 0 can be broken up into 1 over 10 multiplied by 1 over cosine squared x, because that's secant squared. I secant talking. Okay, this yields through the method of direct substitution 1 over 10 multiplied by 1 divided by cosine squared of 0, yielding 1 over 10 multiplied by 1 over 1, which, as we all should know, because we're in calculus BC, yields 1 over 10. Do you have, what did you say? 1 divided by cosine squared 0. Cosine of 0 is 1. Square it. What's 1 squared? 1. 1 divided by 1. See, I'm channeling my mom here.
I'm just letting you know, I took an abstract algebra class in college from a guy that was even more assaulting on my ears than that. Every time he'd ask this question, he'd just look at you like, how can you ask something so dumb? Yes. Caleb, other questions?
Does anybody have any questions?
Give him 1 on 3. 1, 2, 3. Number 2, Willow.
Play on this drum.
That was my job.
Oh, sorry. Oh, I thought you were You were opting out of cheering today
Just got
to
replaced.
get ready for tomorrow.
3.
Okay, number 2. Willow.
You can't say that here.
We're not allowed to. Kids drink it.
Here is the problem, and then because we can't really work with that yet, you split it up into your top and your bottom, in the limit, but since that's equal to 0 over 0.
Correct, right? Yeah.
You take the derivative, and then take the limit of the derivative, which, as it turns out, is also 0 over 0, which is, again, in its determinate form. You have to take the second derivative of each side, which grants you 0 over 2, which is equal to 0. Do you have any questions?
1, 2, 3.
All right, let's take a, okay.
Sean,
Sean,
get out. Guys, it was 1-2.
All right, let's talk about some others. So Caleb, again, I'm worried.
Sit down, boy.
Okay, so,
I have a question.
yes.
If we left the answer at 0 over 2, would that be okay?
It's not wrong, but it could be prettier. I don't know. Do girls do their hair in the morning? It looks just fine either way, but they still do it.
No, it doesn't.
Yes. Well, don't worry. We'll soon we'll have hats at the school, and you'll just be able to cover it up. So, other forms we can make it work for. Now, this is where we have to use our pre-calc, and I need to put that in a different color. So you put it in a different color in your notes. This is where all that pre-calc stuff comes into play. So, and you'll notice I use my Tim Gunn words there. We can make this work. We can make this work. Don't look at me like that. I love my wife. She loves Project Runway. She goes to hockey for me. I watch Project Runway for her. And yes, Tim Gunn says that a lot. So we can make this work, even though it doesn't appear that it's something the Hopi tells. Now, I will let you know, some books are very sloppy with this and call these indeterminate forms. The Hopi tells only works for those two forms, 0 over 0, infinity over infinity. It only works for those two forms. We can make these look like that. We can make these look like that. So we have to use some pre-calc knowledge to do that, though. And that's where this part is hard, because it's a lot of those very dark alleys of pre-calc that were just small problems that come back to haunt us. So let me take a look at that first one. I gave you on the, what did I give you? Yes, we had on the first example, I think it was the limit as x went to 0 of x times the sine of x. Or was it the sine of 1 over x? 1 over x.
What is that from?
Remember I gave you two problems at the start, just kind of see where you were on the Hopi tiles, and then a lot of you looked at me like, what's the Hopi tiles? Now you know, though. Ooh, look how smart you got. Okay, so let's look at this one real quick. What's this limit going to? 0. And what's that limit going to? Infinity is a bad word for it, but it's going to what? Yeah, so this is in one of these forms here. This is in one of these forms here that we will then have to take a peek at what's going to happen to that. How are we going to use pre-calc for that? Yes, Caleb?
That was actually one of the infinity in the original
Oh,
problem.
okay. Because that's better. It was infinity? Are you sure?
Yeah, that would be my,
Yes, it was infinity. Okay, so we've got x times sine of 1 over x. Yes, because that's where it works out. Yeah, that's how it works out. Question. X, as x goes to infinity, is equal to what? Yeah, we can break this up. We can, notice I'm not, we can break this up into the limit of the first thing times the limit of the second thing. That's why it works out. I was thinking of problems during the assembly that would be awesome to work in class today. Now, question to you guys. The limit of x goes to infinity of x is going to go to what? It's going to go to what? Infinity, right. Infinity. 1 over infinity is going to get really close to what? 0. What's the sign of 0 going to? 0, right. The sign gets, as 1 over x gets really close to 0, the sign will get really close to 0 because you're plugging in something that's getting closer and closer and closer to 0. Now, the problem is that a form of L'Hopital's? It's not. What can we do? What can pre-calc do for us on this one? Because we have to turn this into a what? Fraction. Question. What could we put in the denominator that would give us the same thing but just look different? What could we do to put something in the denominator to make it look different but be the same thing after all? Talk to the person sitting next to you for a minute. What can we do to get, because we got to take one of those two things, we got to put it in the denominator. What can we do to put one of those two buckets in the denominator and still make this the same thing that it is right now? What could we do?
With one of those two things?
Yeah. Well, because L'Hopital's only works if it's 0 over 0 or infinity over infinity. So you got to pick one of those two. So we're either going to make it 0 over 0 or infinity over infinity. Which one? Which one? Yeah.
You start giving up later.
Oh, but your hands stink on it. Oh, it's just a grossy one. Grossy one.
You just start-
I,
I have two things to say this.
but I don't even claim to be like half as cool as Mrs. Carpenter, so.
You know what?
I don't even claim to be half as cool as Mrs. Carpenter.
Why did she give you
But
guys that?
I have a worse grade in mythology than I
That's an achievement.
That's hard stuff. All right, ideas. What could we do? What could we do? Yes, Ariana.
We can put a 0.
If we put a 0 in the denominator, isn't the whole thing undefined though? What could we do who's, wait for it, not put a 0 in the denominator, but make the limit of the denominator, right? Use the big word, denominator. The limit of the denominator be 0. Ideas, thoughts. Yes, Napur. Oh, yes, Nick.
You can multiply the full function 1 over x over 1 over x,
1 over x by 1 over, oh.
which is a fancy term for 1.
Yes, I was even thinking of doing it more simply than that, but that's even better. Let's do that. So we're going to multiply this whole thing by 1 over x over 1 over x. Ah, genius. Nick Shampoo. Look at you.
But this wouldn't work for every problem.
Well, this is where we are, like I said, this is where you channel your inner Tim Gunn. We make it work. We got to get it in one of those two forms, either 0 over 0, infinity over infinity. Here's my thought process on this one. I don't really want to think of a way to move that to the denominator. Not even close. But this is probably easier to move to the denominator. This is probably easier to move to the denominator, which Nick said I can move it to the denominator if I multiply the top and the bottom by 1 over x, 1 over x. I've taught this probably 10 times. I've never thought about doing it that way, but that's actually pretty ingenious. So I had x, sine of 1 over x, 1 over x, multiply the top and the bottom by 1 over x. Now it turns out, what's 1 over x times x go to? Right, goodbye. So now I can break this up into the limit as x goes to infinity. Nick Shampoo, how smart are you? Yeah. The top going to? Well, let's plug it in again. If we plug in a really large number, 1 over a really large number is going to get really close to 0. Sine of 0 is going to get really close to 0. 1 over x, as we plug in a really big number, is going to get really close to 0. Right. So now, ooh, good news. Now we have a what? Indeterminate form. Right. We have an indeterminate form. So now we can take the derivative of the top over the derivative of the bottom. Question to you guys. The top's derivative will be a blank rule. Chain rule, right. Because it's got a what? A function inside of the function. All right. So let's take a look. So now we use L'Hopital's, which I always write L''H. Every time I use L'Hopital's to let my reader know that I'm using L'Hopital's rule. Really? That was funny to you all. If that's not a sign you all are total nerds, I don't know what is. If that's not a sign you are total nerds, I don't know what is. Okay, so I use L'Hopital. So the limit of the top. Don't get that into my head because then I'll start saying it. Okay, what's the derivative of that? Well, the derivative of sine is what? Cosine of 1 over x multiplied by that. 1 over x is really x to the negative 1. Remember that. 1 over x is really x to the negative 1. So power base, 1 less power. Okay, the derivative of the bottom, power base, 1 less power. Look what happens there. Look what happens there. They cancel, right? So now this is just, that, okay, really? That got you excited that I said L'Hopital? Can't even say it right. L'Hopital, but that didn't get you excited? Okay, so this is really equal to the limit as x goes to infinity of the cosine of 1 over x. As x gets really, really, really big, what's 1 over x get close to? What's the cosine of 0 get really close to? 1. So notice, this does not look like a L'Hopital's problem initially. We have to make it work. But how do we make it work? We got to move one of those things into the denominator. I would have told you that just x is the same thing as 1 over x, but actually, I Shampoo did it anyway, so that worked for me. We'll do one that we have to use the logarithms for in just a second, but questions on that? Questions on that?
This wouldn't work for everything.
No, and this is where I emphasize this. L'Hopital's can be really easy if you just teach it with problems that work out really well. But it also works for those 5 other forms where you really have to dig into pre-calc to remember how to do that. So don't just think like this only works if I have a rational. It also works if I have some of those other indeterminate forms, but I have to make those work. And they are challenging. And I got 10 minutes left. Which one do I want to do? Which one? Okay, I will tell you, one of the strategies you can use is making a common denominator. Like if you've got two things that are fractions that are being subtracted, you can make a common denominator between the two, and that's another way to get it into that L'Hopital form. But let's take a look at one of the ones that'll just mess you up for tonight. So let's take a look at a bugger. Let's look at a bugger. A what? Yes. Ayana, it's a disservice to the smartest kids in the school if I don't make you smarter. Yes, I did. But that, in fact, I regret doing that. I should have just said, hey, I'm going to give you a 30-second intro to this and then just freaking memorize it. Like, I shouldn't have spent a day on that. That was bad of me. Okay, let's take a look at a really fun one, though. Let's go to the limit as x approaches 0 from the right-hand side only, and you'll see why it's the right-hand side as we work the problem, of 1 plus x to the power of 1 over x. Oh, sorry. Yes. Example, is this 4 or 5? 6. Well, this is the next one. How about example next? It's a great problem. I love this one. It's so beautiful. So beautiful. So let's talk about the form. We're approaching 0, which means we're plugging in numbers that are really, really what? Small. So we have 1 plus something really, really small. What's that going to get close to? Yeah, it's going to get close to 1. 1 plus something really, really small is going to get close to 1. But the numerator, or the power, 1 over x, is going to get really, really what? So we have a number that's closing in on 1 to an ever what power? Growing power. So you've got something that's diving into 1, but it's being raised to a very large power. So the exponent is getting close to what? The base is getting close to. Now, you'd obviously say to yourself, the answer to this one is what? Well, yeah, 1. The 1 would, because 1 to any power would give you what? Right. But this one, let's take a peek at what we got to do for this. This is an indeterminate form. 1 to the infinity. I know you're really tempted to say it's 1, but it's not 1. It's getting really what to 1? Does it ever actually get there? No, you plug in 1 quadrillionth. It's still a little bit bigger than 1. You can't use the properties of 1 for something that's close to 1, but it's not there. So you can't just assume I'm multiplying 1 a whole bunch of times. You're using something that's getting really close to 1, but raising it to an increasingly large power. So don't be tempted to use the properties of things that are equal to 1 to something whose limit is 1. So we have an exponent. How do we get rid of stuff in the exponent? Yes, we got to turn this into a log. So we're going to do some pre-calc work to the side. Like I mentioned, the hard part of this is really that pre-calc part. So we're going to do some pre-calc. We're going to set 1 plus x to the 1 over x is equal to y. Realizing that the limit as x approaches y from the right will equal the limit as x approaches now, a little bit weird. This has a y, but the limit is still what? It's x, right? It's still going to 0, but it's still an x value. We can't just randomly plug in variables. Like I told you earlier this year, once we let something be something, we got to be it. Okay. So now let's take a look. We can still use this to apply the limit. So if we can find the limit of this, this will be equal to it. So let's go back to our pre-calc. Y is equal to 1 plus x to the 1 over x. Somebody said I'm going to take the natural log of both sides. That's probably a pretty good idea. Natural log of both sides. So I have the natural log of y is equal to the natural log of 1 plus x. What am I going to do with the 1 over x? Bring it down in front.
So why did you put those limits in there?
Because I am saying if we can find the limit of one of these two, that's what the other limit's going to be equal to. And I have a feeling like the algebra is going to work itself out where we have to do something there. Okay, now let's relook at the let's look at this real quick. What could I do with that x? I could put it down in the what? Denominator. And now you're kind of feeling that since you've done it a few times. Now it's going to be in what form? One of those indeterminate forms you can use the L'Hopital's for. So now let's just manipulate this side real quick. So I've got the natural log of 1 plus x over x. Remember, that's not equal to y. That's equal to the natural log of y. So now I'm going to take the limit of both sides. Okay. A really dumb question, but this limit, do I know what this limit is? No, so we're going to have to manipulate this side. As x gets really small, 1 plus x will get really close to. And what's the natural log of 1 going to get really close to? 0, right. As you plug in numbers that are getting infinitely close to 1, the natural log of that is going to get infinitely close to 0. So we at the top we have 0, and then of course as x approaches 0 from the right, x is going to get close to 0. Now a duck question real quick. Why do we not consider both sides of that? Why do we only consider 0 from the right? You said that in the problem, but why do you think it only does the right-hand side?
Because of the negatives.
Because the negatives, yes, and the natural log's derivative is not continuous at that point. Okay, so we've got that. So we can take the derivative of the top over the derivative of the bottom. So the limit as x approaches 0 from the right, what's the derivative of the natural log? 1 over what's in there? Yep, so 1 over 1 plus x. Derivative of x equal to 1. So now this is just the limit as x approaches 0 from the right of 1 over 1 plus x, which is going to get really close to what? 1, right. Okay, I'm not done. And I hope you realize why I'm not done yet, but I'm not done. Questions for you guys. I'm just getting to that point right there. Questions on getting to that point right there. Now that is equal not to y, but to the limit of the natural log of y. So let's bring that down. Okay, question, what's that limit equal to? Can somebody, oh, thank you, whoever just said that. Can somebody read it to me real quick? Just volunteer. Somebody read that line to me right there. Yeah, Stefan, thank you, beautiful. Question, what does x approaching 0 have to do with the natural log of y? Nothing, right. So what's that limit equal to? Question, Stefan, can you read it again to me one more time?
Limit is x approaches 0 from the right of ln of y.
What's getting really close to 0? Does that have any effect on that? No, because where's the x in that one? There isn't one. And that's like a Calc 3 idea where you have to think, if I'm taking dx, everything else is going to temporarily feel like a constant. So what's the limit of a constant? What's the limit of the constant? It's just ln y is equal to 1. Okay, how do you solve that? Yeah, what's the base of that? So e to the 1 is equal to y. So what's y equal to? E. So what's the limit of that puppy equal to? E. Because look what we did. We set y equal to that. If the limit of that is equal to something, the limit of that is equal to something. We just used some pre-calc to get that stuff out into one of those indeterminate forms. Once we got it into that indeterminate form, we found that that side was equal to 1. This side is the natural log. It's equal to 1. Change the formula. So e to the 1 is equal to y. So what's the limit? The limit's equal to what? E. The limit is equal to e. I keep using y. Yep, Caleb.
So could we use this method to find e using the 1 plus 1 over x?
Absolutely.
X? We could use this method.
Absolutely. Ayana.
If we go back a step, it says that there's probably not Stefan right now.
Yep.
So we plug this back in.
Plugging back in is not the right word for it. We evaluate the limit of this side, which I saved because what's changing over here? X, but we don't have any x's. We have a y, which is a very Calc 3 concept that if we're taking the change in x, we treat all the other variables temporarily like constants. But that x going to 0 has no effect on y, so it's just equal to the ln of y. Change the base, e to the 1 is equal to y. So if y's limit is equal to 1, if y's limit is equal to this, and this is going to e, what's this also have to go to? E, right. In fact, Caleb, are you ready? This was the first definition of e.
And then the other definition was?
Just happen to also generate e and be equivalent to that.
I don't understand
Go ahead.
why when we have that form,
Yep.
I can just take off natural log of y equals 1, and work with that. Ignore the limit.
Because the limit is x, not y.
So you can just ignore it.
Right. Ignored is the wrong word, but x changing doesn't affect the natural log of y. Other questions on that? Okay, now, why did okay, I know you're going to see your homework going to be like 4 or 5, because I knew I could teach 4 or 5 in one day, and all the others I was going to be, and I was pretty sure we were going to get out of the assembly late, because we always do. So I know I took it out of sequence, but yes, that's the reason I did it, is I knew I could fit this in one day, and I didn't really want to do a half job of teaching something else in one day. So your homework is in 4.5. I will also text it out. You need to do it. It's on page 338. 1 through 3, they're all true and false. 7 through 15, the odds. And then what else did I give you? 27, 43, 45, then a real bugger, 49, 67, and 71. I picked really good problems. I brought the calculator with me to the assembly. And then the AP ones on page 340, 1 through 4. Now, are these hard? Yes, because so much of that really hard part of pre-calc is in here. So much of that really, like the hardest pre-calc problem ends up being what you have to use to get these to work in L'Hopital's form. Whew, right, Martian. Yeah.
Me too.
Yeah. McCutcheon, present for you.
How long do we have to take it?
To probably December 10th. Yeah.